So as usual, let's start from our classic roadmap, just to have an exact point of where we are right now. So over the last week or so, we started approaching this quadrant of the roadmap. Specifically, we started looking at open loop methods for optimal control. Last Monday, we started looking at indirect methods for optimal control. And we'll spend also today in this box over here and Monday. Then next week, Wednesday, we'll move to direct methods for open loop optimal control. And then we'll move towards closed loop methods in the following weeks. And I just want to make sure that we have kind of the key takeaways in place. And specifically, when on Monday we introduced indirect methods, we essentially said that indirect methods are a way of defining necessary optimality conditions for optimal control problems in their infinite dimensional optimization case. And specifically, again, what I mean by infinite dimensional is that we want to optimize with over functionals, which are, in and of itself, kind of loosely speaking, defined as functions over functions. So we want to find the optimal control u star of t that optimizes a given functional that is given to us. And again, u of t is a continuous signal in the sense that it is defined between some time t0 and tf. And again, loosely speaking, it represents to optimizing the full kind of control signal over time. And in order to derive these necessary optimality conditions, we had to extend basically everything we know from the kind of domain of finite dimensional optimization, and essentially derived kind of a key result, which is the fundamental theorem of calculus of variation. So these slides are not the ones you will find online. These are just some selected slides from Monday, just to recap. So the key result is this fundamental theorem of calculus of variations, which essentially says that for a function x star to be an extremal, so loosely speaking, kind of a local minimum or optimum for our functional, the variation of j must vanish at x of star. Namely, we derive this equation here, that the variation of our cost function j evaluated up the optimal x of star needs to be 0 for all admissible variations delta x. And kind of in your mental map, something that I want to stress is that this condition here, when we map it to the finite dimensional case, should essentially feel as if we are saying that the differential is equal to 0. So that the gradient of f transpose delta x is equal to 0. Now, this result is obviously important because it characterizes what is a local minimum in our case, in the case of infinite dimensional functions, but it is not actionable. So what we did on Monday is that we took a specific simplified optimal control problem, which is essentially the one where we were assuming to have a functional defined through this stage-wise cost g, which is a function of x of t, x dot of t, and time. And so essentially speaking here, we refer to it as simplified because if it's as is, we are directly controlling the state trajectory. So no explicit controls u in this case. And we were assuming, and we essentially derived kind of from the fundamental theorem of calculus of variation an actionable strategy to solve this problem and to define necessary optimality conditions. And of course, we did this in the case where both the initial and final conditions were fixed. So the initial time and final time were fixed, and the initial state x and final state x at tf is also fixed. And so we started, if you remember, kind of a derivation where we took the increment of the functional, we linearized, so we took the linear part of that increment, and then we derived a condition on that linear part of the increment, which boiled down to the Euler equation. Essentially, here is where we kind of fast-tracked Newton in just one lecture, essentially. And here is where I want to now delve a little bit deeper, because we didn't have time on Monday, is that this Euler equation is, again, in your mental model, you should essentially see the Euler equation as the analog of the gradient of f equal to 0 condition in the finite dimensional case. Because now this is actionable, right? We can actually compute this. Now let's look a little bit closer at what this Euler equation looks like. It is a nonlinear ordinary differential equation, specifically a second-order differential equation, because here we have a function g of x dot that is also differentiated with respect to time once more here. And specifically, it is an equation with split boundary conditions. So now you might be more familiar with kind of the type of differential equations which are regarded as kind of in the form of Cauchy problems, where usually the boundary conditions are only one-sided, for example, at the initial time 0. But here is, if you wish, this is a slightly nastier object, because in this case, the boundary conditions are split. So we have them both at the beginning and at the end of time, in this case. OK. Any questions on this point? Yes?
Can you re-explain why it's okay to use reliably instead of like an optimal control sequence?
Yeah, so this is derived on this kind of simplified setting, where we are assuming that we can control the kind of the dynamics, if you wish, as if we are directly controlling the state trajectory. In the next slides, we will kind of relax some of these assumptions and build towards an actual optimal control problem. OK, so what we'll do now is I'll spend maybe 5 minutes or so doing a concrete example of how to use these optimality conditions in practice. And then we'll move towards relaxing these boundary conditions and these simplifying assumptions that we just introduced here. OK. And specifically, the problem we'll be looking at is the one of finding the minimum shortest path between 2 points. So even just to build kind of a mental map, assume we are at a specific time 0 and x of 0. We want to find the shortest line that connects these two points. And it will give us kind of great satisfaction in deriving the fact that this is actually the straight line. And the way we will do this, of course, is by leveraging calculus of variation. So remember that, first of all, to approach this problem, we have to define what is a functional that represents kind of the minimum distance between these 2 points. And remember from kind of your calculus classes that in order to measure the length of a line, what we do in practice is that we take a kind of infinitesimal segment ds, and then we integrate it over the entire length of the line. And so for us, kind of we will define the length of the segment is something along the lines of taking this infinitesimal displacement and just integrating it over the length of the line. Now, how do we calculate this in practice? As usual, we are often only good at handling linear objects. And so assuming that kind of ds is small enough, we do this by taking an infinitesimal displacement in time, which I'm calling dt, and in the x direction, which I'm calling dx. And so from using Pythagorean's theorem, we can approximate ds as ds squared equals dt squared plus the delta x squared. OK. From this, we can, of course, derive the fact that delta s is equal to the square root of dt squared plus delta x squared. Taking delta t out of the square root, we will get that delta t multiplies the square root of 1 plus delta x over delta t squared. And assuming there are no mathematicians in this class, here we are kind of redefining this as x dot. And so this leads to kind of our definition of the functional j as the integral between t0 and tf of our equation that we just derived for ts, which is essentially the square root of 1 plus x dot of t squared in the t. And this is essentially our g of x dot t. Yeah. OK. So now to solve this, we want to be methodical. So we want to apply Euler equations, or necessary and optimality conditions. So to do this, what we need is to, first of all, compute g of x and g of x dot, which, as a reminder, so g of x is equal to the derivative of g with respect to x, which in this case, the g does not depend on x. It only depends on x dot. And so this is equal to 0. The next thing that we need is indeed to define g of x dot. Which is 1 over 2 multiplied by square root of 1 plus x dot squared times 2 times x dot. The 2 cancel out. And so for us, g of x dot is essentially x dot times 1 plus x dot squared power of the negative 1 over 2. OK, so here we're just basically computing those terms that we need in order to apply the Euler equation. OK. So now what we want is, indeed, just computing that and spelling out that Euler equation. So what we need is to compute the derivative. So we know that the first term is 0. And so what we need is the derivative of g of x dot with respect to time, which is equal to x double dot times 1 plus x dot squared to the powers of negative 1 over 2. Plus the derivative of the second term, which is indeed x dot multiplied negative 1/2 times 1 plus x dot squared to the power of negative 3 over 2. Multiplied by the derivative of the term inside, which is 2x dot x double dot. Again, just some derivations here. Now, we can rewrite this as x double dot over 1 plus x dot squared to the power of 1/2 minus x dot squared times x double dot over 1 plus x dot squared to the power of 3 over 2. Which we can rewrite as x double dot plus x double dot times x dot squared minus x dot squared x double dot. Everything over 1 plus x dot squared to the power of 3 over 2. Which finally is equal to x double dot over 1 plus x dot squared to the power of 3 over 2. OK, so now basically what we have is we have both of the terms that we need for our Euler equation. And essentially, we can then write our necessary optimality conditions as the fact that, so g of x is equal to 0. And so we can write that x double dot has to be over 1 plus x dot squared to the power 3 over 2 needs to be equal to 0. Now, we know that this is always positive. And so the only way for this term to be equal to 0 is that x double dot has to be equal to 0. And so we essentially reach that this is now our Euler equation kind of fully fleshed out. which needs, of course, our boundary conditions, which in our case are that x of t0 is equal to x0, and x of tf are equal to xf. Again, here we didn't really specify what x0 and xf are, but this is where what the boundary conditions look like. Now, this is something we know how to solve. So what is the solution here when we integrate x a double dot equals 0? Yes?
It's a straight line since there's no concavity.
Yeah, exactly. So kind of writing it down, it means that x of t is equal to c1t plus c2, which it is indeed the basically the formula of a line, right? The equation of a line. Now, notice that here we have, again, kind of pointing your attention to the fact that this is a second-order differential equation. This will need kind of two constants of integration that we need to pinpoint. And so here we're using our two boundary conditions to pinpoint those constants of integration. And so we indeed proved that the shortest path between 2 points is a line. Now, formally, what we proved here is that the line is a candidate for optimality. There are kind of second-order arguments could be done here to actually prove that this is an actual optimum, but this is the kind of way mechanically in which we would use these conditions. Okay. All right. Now, if this is clear, I would move towards what is probably the most interesting for us and for the purpose of this class, which is wanting to now apply these ideas towards an optimal control problem. And to do this, we need to expand and relax some of these assumptions we're doing to simplify the setup. Yes?
Again, this the x dot is 0 boundary condition. Oh, is that an x double dot?
Where, sorry?
Oh, it's a double dot.
This is double dot, yes. Yes, Ellie made sure that the markers are all nice and working today. So.
Didn't you just integrate it, right? So once you have that x double dot at 0, you literally just the integral. Yeah. Okay. Very good.
All right. Okay, so this is the mechanics of how you would use kind of the Euler equation, essentially the optimality conditions for the case we're looking at. And now we want to build towards problems that we actually care about solving, which are optimal control problems. And so the first kind of extension that we want to do to this formalism is relaxing the assumptions that the boundary conditions are fixed. So we derived all of this using the fact that initial time, final time, initial state kind of condition, and final condition were fixed. And so we want to relax this assumption. And so what we do here is we take the exact same setup. Now, formally, we're considering functions which map reals to reals in Rn. So we're just like a multidimensional version of that, but it shouldn't bother you. It's exactly the same thing. With the usual assumptions, we're assuming that G is twice differentiable. The initial conditions, T0 and X of 0 are fixed. But now we are relaxing the fact that the final time and X of Tf might be fixed or free. And so essentially, what we want to do here is kind of adjust our optimality conditions in order to handle these cases. Now, the problem here, as you can probably imagine, is that, so we showed here already on this example that the optimality conditions boils down to solving these differential equations. And in order to solve them, we need to pinpoint kind of some constants of integrations. And here we use the fact that we had these boundary conditions fixed to pinpoint those constants of integrations. But the moment we are relaxing this, we are missing some boundary conditions. So essentially what happens here is that the Euler equation remains valid, so it still has to hold. But now we're lacking these boundary conditions to pinpoint the constants of integration. And so this is kind of in general for today. I will be limiting myself to stating the results We'll be proving also some of them, but most of the proofs are, one, very similar to the kind of manipulations we did on Monday, and so not very insightful in and of itself. And so I will focus on stating the results and showing you how to use them. And so the fact here is that we need to have a more sophisticated version of the boundary conditions. And specifically, the boundary conditions are found from this equation here, which, at the first approach might seem like a very nasty equation to deal with. So let me unpack it and show you how to use it. So first of all, notice that here we have these two terms, which comprehend kind of these delta xf and delta tf. So we have the variations in xf and the final time. The trick here will be that we will have to make the appropriate quote-unquote substitutions for these delta x terms. And so very practically, if we are in a setting where delta x, again, delta x here represents the admissible variations that we can allow at the final state, xf. So if delta x is fixed, it means that the only admissible variation here is 0. And so this entire term will go to 0. And so we're only left with this other part of the boundary condition. Same thing for delta tf. So we'll be using the fact that either one or the other are fixed or free in order to basically compute the additional boundary conditions from this equation over here. And you can imagine there are a number of different cases. We won't go through all of them, but there are some nice tables which basically summarize all of the cases that we can find and different combinations. So for example, if we look at the very first one, this is the setting we were on Monday, and in the example that we just showed, where both xtf and tf were specified. And so this essentially entails that the boundary conditions are the initial and final state in and of itself. On the other hand, if the final x of tf is free and the final time is specified, what we get is essentially that the derivative of g with respect to x dot evaluated at the final time needs to be equal to 0, which is indeed only this part here, right? So if tf is fixed, delta tf is 0, and so all of this gets canceled out. And so what remains is this part over here. And so we know that if this is free, so we can have any admissible variation, in order for all of this to be equal to 0, then this part has to be equal to 0. Okay, so nothing too crazy here, but at the very high level, what we're doing is that we are extending the current formalism. When we extend it to generalized boundary conditions, we are lacking some boundary conditions to pinpoint constants of integrations. And we can derive them through this equation over here, which ends up being kind of a case-by-case analysis on essentially pinpointing those constants of integration. Does this make sense? Okay, great. So now, again, to kind of see this in practice, how this works, let's take a very related problem in a way.
You're talking about your boundary condition. Notice that the initial time at enter, is that you're always assuming that to be set.
Sorry, can you repeat?
I noticed that the initial time for the x is not in there. It's only whether or not x at the tf are set. Is that because and it also didn't show up in the equation, but it's always set as being initial. So are we assuming that's always fixed?
Yeah, I mean, usually if you think about it from an optimal control problem, you know where you are now and you know what time is
Sure. Okay,
yeah.
but there could be also some problems where it's when you're going to start necessarily measuring or something like that perspective, or it can start at any time if you're thinking maybe not from an AA point of view, but maybe from a optimizing some type of point in when you're going to make this decision or something like that perspective. But then we wouldn't be able to use this method.
I think you can always reformulate your problem such that you're starting from 0, times 0 and state 0. You can always reshift and reorient your problem to always have the initial conditions that are given. Does it make sense? Yeah. Okay, and so the example we'll be looking at specifically is one where we want to determine, again, the smooth curve of smaller length that connects point x of 0 equals 1 to kind of a free final point, x of tf, but on the line t equals 5. So here we're assuming we have a fixed final time of t equals 5. We have a fixed initial condition, x of 0 equals 1. But then we want to find the curve of kind of shortest length that connects to this line here. So we want to find the final x of tf. So it could be this line over here. It could be this line over here. It could be this other function over here. But most likely, it'll be this one here. Right? And so let us now approach it from the perspective of the optimality conditions which we just introduced. So again, as we were doing here above, the cost functional will be the same. So we keep this cost functional over here. And we already applied the Euler, so we know from the treatment we were doing here that the Euler condition still holds. Right? So we can leverage the results that we had here above, meaning that the Euler condition essentially boils down to this equation over here, right? Which, just for practicality, let me rewrite. So we derived above that x of t is equal to c1t plus c2. Now, in this case, we have one boundary condition, which is that x of 0 is equal to 1. And so from these two, we can evaluate x at time 0, which is equal to c1 times 0 plus c2. And this must be equal to 1, right? Which essentially means that c2 is equal to 1, right? So we used the initial condition to pinpoint one of the two constants of integration. Now, how do we find the other one? So c1. We are missing, as we were saying before, one of these boundary conditions, and so we'll use the one we just derived on the slide. And again, we want to be methodical. So the way we do this is that from the table, we are in the case where tf is specified, but x of tf is free. So we already used this boundary condition over here. Now we want to use the second one. Okay, which in practice boils down to evaluating the variable g with respect to x dot, which we did again before, but let me just rewrite it here, which is 1 over 2 multiplied square root of x, 1 plus x squared. X dot squared times 2x dot. And so what we want in practice is that we want to take this expression, so looking at the boundary condition, we take this expression, we evaluate it at time tf, and we set it equal to 0. So this leads to x dot of tf over square root of 1 plus x dot of tf equal to 0. Which essentially means that x dot of tf is equal to 0. Right? So now we know from here, we know that x of t is equal to c1t plus 1, because c2 is equal to 1. Which essentially means that x dot of t from here is equal to c1, right? By differentiating this. And so basically now what we have is that by combining these two, we can essentially derive that C1 is equal to 0. Because we are evaluating this at the final time, and we know that this is equal to 0, so C1 must be equal to 0. Right? So now what we get, kind of as a final result, is that we pinpointed both of our constants of integration. And so we have that C1 is equal to 0, C2 is equal to 1. And so we get that x of t is equal to 1, which is indeed this line right here. Again, nothing too deep here. It's exactly the same mechanics. I just showed you an example of how do we derive those additional boundary conditions in the moment we don't have the necessary boundary conditions that are needed. Okay. Okay, so in general, just as a caveat, the moment we have kind of multi-dimensional functions that we're dealing with, the exact same mechanics apply. We just apply them component-wise. So again, nothing really deep here. We used everything assuming we had functions that mapped reals to reals. But in the moment where we have multi-dimensional functions, we would apply all of the boundary conditions and all of the Euler equations per component. Okay, the second extension that I want to briefly touch upon, I say briefly because we will be expanding on it in the context of optimal control in a few slides from now, is the one where we are considering constraints that link together the function, Wt in this case, with the derivative of the function Wt with the function itself. Yes?
Just on that example, I might not be seeing something, but I'm wondering how you got x of t equal to 1 and not x of t equal to a constant.
Because we pinpointed this constant of integration. This one here, where is it? Yeah, C2 equals 1. Okay. Right? So we know that x of t is C1t plus C2, and we pinpointed both. C2 is 1 and C1 is 0. And so you get that x of t is equal to 1. Okay. So again, what we're doing here is we want to bring forward a second extension that we're doing to the current formalism. Specifically, we're interested in having extensions to the fact where we have constraints that tie together the derivative of a function with the function itself. And so here we're considering a situation where, say we have a function w that maps reals into Rn plus m, where we want to essentially find the extrema for w star that basically optimizes this functional over here, which is the exact same situation we were seeing before, but now we have everything expressed in this w. Now notice that the constraints here are only with respect to the first n dimensions. So w is a function that maps in n plus m. We have n constraints. And so kind of, if you wish, kind of a way you can interpret it as taking a step into the direction of what we care about is that n could be our state dimensions, m could be our controls. And so we have a constraint here which represents the analog of the system dynamics, which essentially ties together the controls, which are the m free variables, with the n states.
When we were previously doing assuming x was like a number, now you're calling it w, making it a vector, and then you're also adding.
Yes, exactly. So if you wish, the extension of calling it w and being it a vector value function is just extending from functions that map real to reals into vector value functions. The only thing that we're adding here is this type of constraints. Yeah. Okay, and so indeed, we mentioned that only m of the n plus n components of w are independent, and constraints of this type may represent the state equations, such as the system dynamics. And so indeed, maybe one way to interpret it is just W is the concatenation of our states and controls variables, control functions. And so the way we handle this is similar to the way in which we handled in finite dimensional optimization the constrained setting. And specifically in finite dimensional optimization, if you remember, we introduced the concept of Lagrangian, where essentially we took the constraint, we added it to the objective function together with some Lagrange multipliers, which we called lambda. And then we treated the problem as if it was unconstrained. So essentially, this term represented like a penalty for violating those constraints. And so here, what we do is exactly the same thing, in the sense that we posit an augmented integrand function g, specifically g of a, which is the original g plus this term here, which represents the constraint, multiplied by this p of t, which is the analog of the Lagrangian multipliers. Now, notice that in the finite dimensional optimization, lambdas was just a vector of values. Now, p of t is a function of time in and of itself, and is usually referred to as the costate in literature. Costate because you have one function for every state that you have in your system. Yeah, again, so we're changing the notation because this is what you will find in literature most commonly, but this is exactly the analog of the lambda variables that we introduced in finite dimensions. Okay, so the point here is that we are extending our necessary optimality conditions to various extensions. And so what you get is that the optimality conditions for this case, so the case where we are introducing this kind of constraints, essentially boils down to enforcing the Euler equation, this time on the augmented cost. So again, we're using the exact same trick we did in finite dimensions. So we took the constraint, we added it to the objective function, and we're treating it as if it was unconstrained. And so this is exactly the same thing that we're doing here. We're taking our differential constraints, adding them to the original cost function g, defining the augmented cost g of a, and applying the Euler equation to this g of a. Of course, here there is an additional condition, that is the fact that the constraints must be satisfied. Right? So if a function is optimal, it has to be also satisfying those constraints. And indeed, notice again the similarity with respect to the finite dimensional optimization. Again, this I just wanted to kind of share the intuition of how we deal with this. We'll formalize it in a couple of slides. Okay, and so given these two extensions, we were treating them from the broader perspective of calculus of variation, which is this tool, kind of mathematical tool we're using to solve problems over functionals. But now we want to go into things that we actually care about, which is solving optimal control problems. And we will do this in kind of 3 steps, actually 4. Today we'll only look at the first one, which is we will be deriving necessary optimality conditions for optimal control problems, assuming that the controls, admissible controls, are not bounded. So we won't be assuming controls such as constraints such as maximum thrusts on the controls. On Monday next week, we'll be introducing kind of the celebrated Pontryagin minimum principle, which is essentially the generalization of these optimality conditions to the case where the controls may be bounded. And then we will apply these optimality conditions to a number of known cases, showing that we can derive known strategies for controls, such as bang-bang controls, to those of you that are familiar with that. And then the fourth that is not listed here is that we will be looking at computational methods for solving these differential equations. So until now, we've solved these problems analytically, if you wish. In practice, how you will use them in this class and potentially in your career is that you will be using the optimality conditions to derive these differential equations. You derive the boundary conditions for your specific case, and then you feed both, so the differential equations and the boundary conditions, to a numerical solver, which will take care of the solution for you. And so this is why indirect methods are also called optimize then discretize, because here we're formulating the optimal solution, so the optimized part. And then the discretization part usually comes when you feed this into a numerical solver. Does the plan make sense? And any questions so far? So let us consider now the optimal control problem with unbounded controls. So specifically, as we introduced also a couple times in the previous lectures, the problem here is we want to find an admissible control, U star, which causes the dynamical system, represented by this differential equation, to follow an admissible trajectory x of star that minimizes the following cost functional. The cost functional is composed of two terms. Stage cost, represented by g, which is a function of x and u and time. Usually, g is something that is accumulated over time and could represent things like control effort. So maybe something like u squared. So you don't want to maybe push too much on the throttle or something like that. And terminal cost, which depends only on the final time, so the state at the final time. And this could represent something like making sure that you're actually hitting the target that you want to hit. Notice that J, so the cost, is only a function of U. Because this U are our free variables, our controls, and the state that corresponds to our control signal are kind of implicitly defined through the system dynamics. So this is the setup we introduced before, but just making sure that this is exactly where we're going into. And we're assuming that the initial time and the initial conditions are fixed. Okay, so the way I will go by deriving the optimality conditions is in 3 steps. So first, I'll state them. Then we'll go through an example showing how to apply them. And then we'll go through a sketch of a proof of how we can derive these results. So the optimality conditions are nothing more than this slide, nothing less than this slide over here. So specifically, the optimality conditions state that we define the Hamiltonian, meaning we augment the cost with the constraint. So exactly how we did before, through the kind of equivalent of the Lagrangian, our co-state variables, P of t. And then kind of define the optimality conditions whereby an optimal x, p, u triplet must satisfy some differential equations. We'll have a look at them more later. Given some boundary conditions, which are given through this equation over here, which we can handle exactly how we did before, depending on if our final time or xf are fixed or not. So let's have a look a little bit more closely at what these differential equations look like. So the first one is obvious, because these are essentially the dynamics constraints. So if you look at the Hamiltonian here and take the derivative with respect to the co-state P of t, what you're left with is that you're left with the dynamics. You're left with f, right? So essentially, this condition over here is just saying that for a triplet to be optimal, it needs to satisfy the dynamics. Makes sense. The second and third are less intuitive. We'll derive them in a bit. But very mechanically, what you typically do is that you would essentially define the Hamiltonian. You then posit these differential equations. You use the third, which are M algebraic equations, actually. This is not a differential equation, to express U as a function of P and X. And then you basically solve these differential equations using the boundary conditions to pinpoint the constants of integration. Yes? Yes, so it's a good question. It's important that this is clear. So remember how we were looking before at the case where we introduced the constraints represented by the dynamics. And in order to handle these, we used kind of a very similar logic that from the one that we used in finite dimensions, which is when we have a constraint, in order to handle it, we take that constraint and we augment the cost with a penalty for that constraint, and then we treat the problem as if it was unconstrained. And so in finite dimensions, we did this through Lagrange multipliers, which are the lambdas, if you recall. And the co-state here is playing the exact same role, but this time in the context of continuous time functions. And it represents the analog of the Lagrange multipliers, which we call co-state, and label them as P. Does it make sense? Any other question on this? So again, here I'm just stating what the optimality conditions are for the optimal control problem we are interested in. And these optimality conditions look as this set of differential equations with accompanying boundary conditions. And mechanically, we will see how to use them, but it is mechanically, it's kind of a process where we compose the Hamiltonian by essentially augmenting the cost through our dynamics. We define these differential equations, and then we solve for them by using the boundary conditions. Okay, as we were doing before, of course, in order to find the correct boundary conditions, it's also a case-by-case scenario, and so we have kind of equivalent tables as we were having in the previous case. Yes.
I also had a question about the previous slide. Could you restate you were saying something? You solve the last of the two for you, and then do something like that?
Yeah, so we'll see it in a moment because we'll do an example. But what I meant is that, so in practice, after you define the Hamiltonian, kind of applying these, so using them to solve a problem, it means that you need to basically solve these differential equations. And in practice, what usually happens is that you use the third one to express u as a function of p and x. And then you use these to basically, feed u in kind of substitute u in the first two differential equations. And then you solve these differential equations, pinpointing the constants of integration with the boundary conditions. Yes?
Just trying to connect what we were looking at before to this here. So we're using like the same boundary conditions that we just talked about. It's just a case of now using these ODEs as well, right?
I mean, the boundary conditions look slightly different as well. So this is where I am just stating the result. I'm happy to provide kind of the derivations of how we get there. We'll have a sketch of a proof, so will be some intuition there. But the point is that the derivations are not that insightful. Yeah. But yes, the point is that you have some boundary conditions which are not exactly the same as we were doing before. Mechanically, we use them exactly in the same way, but they just look different. Yeah.
The difference between what we were previously doing before was a lot of notation didn't just change. The main difference is more, instead of just finding like a position or so, which is x of t, we're now doing it as a control system of equations.
Yeah, so I can understand the confusion that comes with a lot of notation changing. So the point is that up until now, we introduced calculus of variation as a tool for solving infinite dimensional optimization problems, detached from optimal control. And so we were using like only x or w as a combination of everything. Now we are basically doing kind of the hop in the direction of optimal control, and we want to use exact the same tools for now formulating everything, notation included, as an optimal control problem, where we have the dynamics f, we have the states x, and we have the controls u. Does it clarify?
Yes, and so the equations though are slightly changing. Don't have to go like into it, but the equation, it looks extremely similar, and that's on purpose because the only difference is we're adding the u, which like changes it.
What equation are you referring to? This one here?
Yeah, that equation there, essentially, u just became x dot, where it was previously x dot in the previous time, and now it's u, because we are now controlling that versus x dot is decided.
Yeah. If now we are controlling the system
announced?
Through the coupling of, so U, free variables, we control U's, and we control X through U.
Yeah.
Before we could control directly X.
Yeah.
Yeah. Yes?
Sorry, I'm just confused with what's the difference between the Hamiltonian and the GA function that you defined earlier.
Mm-hmm. Yes. So the kind of the GA function, you should see it as I wanted to give you the intuition of how to handle this sort of constraints that couples, in the optimal control notation, couples controls with states. And I did this, here we had like a simplified objective function, right? We only had this G over here. And so in this specific case, kind of augmenting, so kind of taking these constraints into the objective function and penalizing for them, boiled down to this augmented G. In the more general setting, which is the one we care about, we formally define this Hamiltonian, which is, again, intuitively the same thing, but this is the much more general formalism, if that makes sense. Yeah. Yes?
What's the difference between is the Hamiltonian the same as the Lagrangian we had in previous lectures where we had the lambdas and stuff?
You could interpret it as indeed the analog of the Lagrangian. Yeah. Okay, and so in practice, kind of the necessary conditions, meaning these ones here, essentially represent a system of 2n differential equations, of a set of second order, 2n first order differential equations, and m algebraic equations, which is the third. And in order to solve these, we would basically need to pinpoint these constants of integrations. And so we'll do this by using the boundary conditions, as we were doing before. But this is just to give you a sense that at the end of the day, we'll have 2n constants of integrations, and we will need 2n boundary conditions to pinpoint those constants of integration. Actually, so here I'm mentioning kind of 2n plus 1. Can you think of the case where we need the plus 1? So again, here we're just mechanically thinking of, we'll have a set of differential equations, and we need the appropriate number of boundary conditions to pinpoint those constants of integration. We will see it in the example, but essentially the additional one will be to pinpoint the final time. But now I think it's good that we go through an example to see this mechanically. Okay. All right. So the problem we'll be looking at is the one where we are trying to essentially optimize the equivalent of a particle on a line. Right? So we have x of t, which represents kind of our position of our particle at time t. And this is defined by a system which is a second order through some second order dynamics, which essentially means that we are directly controlling the acceleration of this particle. So we're assuming unit mass, and so F equals ma. We are directly controlling the acceleration of this particle. And specifically, we want to steer this system from an initial condition whereby at time 0, so x of 0 is equal to 10, so we are at a position 10, and with 0 velocity, because the derivative of x at time 0 is equal to 0. And we want to reach the origin, so we want that x of tf is equal to 0, and also we want to reach reach it with zero velocity. So this is what we want to do in this system. And specifically, we want to do this while minimizing the following functional, J, which is comprised of two parts. We have a running cost, which is defined as 1/2 the integral between T0 and Tf of bu ut squared. Now, this essentially represents the analog of wanting to minimize control effort, for example. And we have a terminal cost that is 1/2 times alpha Ts squared, which represents the essentially wanting to get to the objective, quickly. Essentially, we don't want to take a very long time, so we're penalizing final time. Now, these two terms are kind of balanced and weighted from these two scaling factors, alpha and b. And so, depending on which one is bigger, we might want to reach our objective by. So if b is very large, we want to do this by not be really cautious with the acceleration that we have. On the opposite, if alpha is very large, we want to reach it very quickly, potentially at the expenses of a larger control effort. Yes?
I just wanted, so you're saying that half part, that just says minimize, so you don't want as much acceleration as possible.
Yes, exactly.
Yeah, I just.
Yeah, indeed. So we are in a setting where we are defining a functional, and in general, we're always minimizing costs in our optimal control problems. Yeah. And in this case, the final time is assumed to be free.
Are these 1/2 squared kind of like generalized how they do the cost, or is that just what?
This is just a choice. Yeah. Okay, so why is this interesting? I think it is particularly interesting because it's a simple example that kind of encapsulates a lot of the characteristics of what you would see in kind of real-world optimal control problems, right? So we have some cost which balances control effort and the final time. We have a free final time which we want to optimize over. And in general, it's a problem that if I were to have given this to you a couple of weeks back, you probably wouldn't have known how to start with, right? And now we indeed have general formalism which we could use to tackle these kind of problems. Okay, so let's get started. So in general, in optimal control, we want to be methodical. So let's apply and follow step by step the recipe. So the first thing that we want to do is define the Hamiltonian, right? Which we defined as G plus our co-state variables, again, the analog of the Lagrangian multipliers, transpose F. Now, in order to apply any of this, the first thing that we have to do is, so remember that you might have noticed, but here we're looking at a second-order system, and everything that we derived so far kind of assumes we have a first-order system. So the first thing that we want to do is cast this problem as a first-order differential equation, which we know how to do. And specifically, the way we do this is by constructing the analog of this system, which is essentially by adding an additional dimension, whereby x dot 1 is equal to x2, and x dot 2 is equal to u. Right? So we saw this, I think, Monday last week. And for us, this here will be f. Right? Okay. Now, remember that we have one co-state variable for every state variable. And so we define P of t as the vector of P1t and P2t. So we essentially have two components. Okay, but so now we have all of the ingredients to define our Hamiltonian. So H will be G, which from our, actually it's probably useful to keep the problem over here. From our definition of the functional, G is 1/2 b u squared. So again, this is g. Plus the vector of costate variables p1t, p2t, transpose x2t, so our f ut, right? Which we can expand as 1/2 b u squared of t plus p1 t x2t plus p2t ut. I hope this is big enough for the ones in the back. Yeah? Okay. Okay, so now that we have the Hamiltonian, let's be methodical and indeed define our differential equations, our optimality conditions. Yes?
Like, let's say it was just we were only controlling the velocity instead of the acceleration. That makes sense. What would we have our f? Would it just be just x itself, and then would there still be the u, or like what would your f be?
Now, I'm not exactly sure about this specific example, but in general, if you have a system where it would be just a first order system, it will be as it is. So you will be ready to apply it.
Yeah, so
Now,
would it still be a two-dimensional? Like,
no, in that case,
just be a p analysis, essentially.
yes. Okay, so let us take and define the first of our conditions, which is that x dot has to be equal to the derivative of the Hamiltonian with respect to the costate vector, which is indeed, we know already this is our f, right? Which, just to spell it out, this essentially means x1 dot equals x2, and x2 dot equals u. So now here I'm omitting t in between parentheses just to save on space, but everything here is a function of time. Okay, so this is the kind of the intuitive one, right? Just our dynamics. Now for the second one. For the second one, what we have is p dot is equal to minus the derivative of the Hamiltonian with respect to x, which is equal to p1 dot. So the Hamiltonian is this guy over here. So taking the partial derivative with respect to x1, so there is no x1 here. So it's just p1 dot equals 0. And then p2 dot, in this case, equals negative p1. Yes, because we're taking the derivative with respect to x2. Yeah. Okay. Does this make sense? Yeah. Perfect. Now, for the third, what we do is that we have set the derivative with respect to the Hamiltonian in the u, which is equal to bu plus p2 from here, which means that u is equal to negative 1 over b p2. So this is, for example, to refer to your comment before, what I meant by, in the third case, we want to express u as a function of p and x. In this case, it's only p. Okay, and so from this, if we kind of are putting these two together, what we get is that x dot 2 is equal to negative 1 over b p2. Right? Okay, so just as a caveat, in general, this is where you would stop, right? So you derive the optimality conditions, you would feed this to a solver together with the appropriate boundary conditions and hope that the solver converges and you're done. Now for the purpose of being methodical, let's try to solve this analytically. Okay, so we know from over there that P1 dot of t is equal to 0. So I'm just rewriting here, which essentially means that P1 of t is equal to C1. So now we're starting to see our constants of integration starting to pop up. So we know from P2 of t that has to be equal to negative P1 of t, again from up there, that this means that P2 dot is equal to negative C1, right? Okay, which essentially means that P2 of t is equal to negative C1 t plus C2. Okay, then kind of, again, going forward, the x2 dot is equal to negative 1 over b times P2t. Again, we got this from over here, so I'm just rewriting it. Which is equal to 1 over b multiplied by minus C1t plus C2, because this is what we just derived. Which essentially means that integrating, we get x2 of t is equal to negative 1 over b times minus C1 over 2 t squared plus C2t plus C3. Okay, so here, to avoid having to carry over this C3 term in the following computations, I'm already kind of exploiting the fact that we know that our initial conditions are fixed. So specifically, we know that, let's just write it here, x dot at time 0 is equal to 0, so we start from a 0 velocity condition, which means that x2 0 is equal to 0. Which essentially means that kind of combining these two, kind of C3 is equal to 0, right? Okay. Actually, let's go over here. Okay. Now, we keep going, and we have that x1 dot t is equal to x2 t. Again, from leveraging our differential equations right there, which is equal to negative 1 over b times negative C1 over 2 t squared plus C2t, where by integrating it, it means that x1t is equal to negative 1 over b times negative C1 over 6 t power 3 plus ct times t power 2 plus c4. Right? Okay, so here we essentially spelled out all of our differential equations. And now what we need is we need our boundary conditions to pinpoint all of our constants of integrations, which in this case is C1, C2, C3, C4. C3, we already used it here, but it's those 4, plus the final time, TF. So we need to pinpoint those 5 constants of integration, and so we need 5 boundary conditions to do so. So again, what do we know? So we know that x1, 0 is equal to 10. We know that x2, 0 is equal to 0. So our position at the initial time is 10, and we are at 0 velocity. We know that x1 at the final time, tf, is equal to 0, and we have to get there with 0 velocity. And so x2, tf is equal to 0. So here we have 4 boundary conditions. And now to get the 5th, we essentially look at our table. And we look at the case when the final position is specified, right? So this one here. So x of tf is a specified final state. And so this means that we need to include this additional boundary condition over here. So what does that boundary condition look like in practice? Is that we need to take the Hamiltonian, evaluated at final time. I'm using this notation to mean evaluated at final time to avoid writing a sequence of parentheses. Plus the derivative of the terminal cost also evaluated at the final time must be equal to 0. So this is our 5th boundary condition, exactly how we got it from the table. So let's just do that. So the Hamiltonian evaluated at the final time is 1 over 2 b u squared tf plus p1 tf times x2 at tf plus p2 tf times u tf. Right, so here I just took our expression of the Hamiltonian and I just evaluated at the final time. Now, we know that this is equal to 0 because we know that x2 of tf is equal to 0, right? From here. And we know that this part over here is negative b ut. Right? From, where is it? Can you spot it? Negative b, well, yeah, from here, for example. Yeah. So we know that P2 evaluated at TF is equal to negative b ut. Okay, and so kind of this essentially means that the Hamiltonian evaluated at the final time is equal to negative 1 over 2 times b u squared tf. So this is the first of our 2 terms that we are computing of our boundary condition. We just need the last one, which is the derivative of the terminal cost evaluated at the final time. Which is equal to alpha tf. So again, the terminal cost for us is this one here. So 1/2 alpha tf squared. Are we able to see over there? I saw you were. Does this help? Yeah. All right. And so basically summing these two parts together, what we get is that 1/2 bu squared tf plus alpha tf must be equal to 0. Right? So essentially we got our 5 boundary conditions. Right? To pinpoint our 5 constants of integration. Yes?
So it's back to the excellent expression in the top right of the bottom right board. Should it be 1/2 C2 v squared?
Yes.
Or is there a reason to do that?
Wait, so you're saying that this should be 1/2, or?
The C2 in the middle of that. Just like inside the brackets, the C2 T squared, should it be 1/2 C2 squared, or on the far right?
Yeah, I see. Yeah, I think you're right. Yeah. It should be like this. Yeah. Yeah, this makes sense. Yeah. Okay, and so basically what happens is that if now we have all of the ingredients and to pinpoint our constants of integration, and what we get is that the solution actually looks like something like this. So we can pinpoint our constants of integration, and specifically we have that the final times look like 1800 times b, divided by alpha power 1/5. Now, while this looks like an okay beast, it kind of aligns with intuition, right? Because so the higher b, so the higher our weight on the control effort, the higher the final time, so we'll tend to go slower. On the other hand, the higher alpha, so the lower will be the final time. So the more we'll be quicker at reaching our final condition. Yes?
For this, if initial condition given by the table, is there any sort of intuition behind it, or should we just take it as is, memorize it, and not worry about it?
Yeah, so this is a great question because it's a great segue into kind of the next slide, which is indeed trying to give you some intuition into how those equations come up. Well, to be exact, the boundary conditions, they're just let's go through this and then maybe we can take this question again. So specifically, okay, so we introduced the optimality conditions. We showed how to use them. Now I want to just spend a couple of minutes to giving you an intuition into how those are derived. Yes?
Yeah, so solve for the final time. Is there a way to solve for the control input time history or no? With that experiment, but we never solved for.
No, well, of course, you would get also once you have everything here from your solver, you would get also kind of a triplet. You would get X, U, and P. Yeah. Okay, and so specifically, so remember how we derived the Euler equation in the unconstrained case? And specifically, our argument there is that we started from the variation. So we took the fundamental theorem of calculus of variation. So that the variation has to be equal to 0, right? And so specifically, we got to here so we turned this into an actionable condition by starting from the increment, taking the linear part of that increment, which equal to the variation. And then we derived a condition on the integrand of that linear part, by leveraging the fact that we could have any potential admissible variation delta x. So this is just at a high level what we did on Monday. So ideally, to derive those conditions, we do a very similar process. However, now the problem here is that those variations cannot be arbitrary because these are coupled together through the dynamics. So the u's and the x's cannot really vary or arbitrary. And so the way we can derive this is that we, first of all, here we consider a simplified setting where we set to 0, the terminal penalty. And we assume that the final time and the x of the f are fixed and given. And in order to derive the optimality conditions for this case, we consider the augmented cost function, which is exactly how we did, which is basically what we did before, which is essentially a trick to basically add 0 to our original cost g. The reason I'm saying that this is a trick is because if you look at this term over here, we have sf minus x dot, and since this is an optimality condition, in order to be optimal, the point also has to be feasible, and so this has to be equal to 0. Right? So essentially, this is a trick where we are defining these augmented costs by nominally adding 0, but we are introducing these co-state variables, or the analog of the Lagrangian, which we will see later. We can then kind of use these in order to select those co-state variables in such a way to simplify our analysis. Yes?
On the previous, how did it go from not knowing u, because that's what we were solving for, to getting, like, of that final circle problem, to getting that t is the 180?
Yes. Do you mind if we take this in a couple of minutes? I just want to go through this slide. Yeah, thanks. So essentially, we are in a situation where the augmented cost function is something that takes this augmented g that we just did. And so by doing an exactly the same process as we did to derive the Euler equation, we essentially rewrite the fundamental theorem of calculus of variation in this, nasty-looking beast. But if you think about it, this is exactly the same thing we were doing in the Euler equation, where we had our partial derivatives of the cost, which we obtained by basically doing a Taylor expansion of our increment. This term here corresponds to the term where we were using the integration by part to eliminate the dependency on delta x dot. And just to make sure that this is slightly more explicit, so this term over here, so the derivative of GA with respect to the costate, is just the term of our dynamics, which we were looking at before. This is equal to negative costate, and this is equal to these two partial derivatives. Now, the argument here is that, as we did before, we want to get an actionable condition by leveraging the fact that the variations could be arbitrary, such that everything inside the integrand has to be equal to 0 in order for the entire integral to be equal to 0. The problem here is that out of all of these terms, the only kind of variations that we could freely vary are the ones in u, because everything else is kind of coupled with respect to u. So what we want to do is that we ideally want to remove all of this extra stuff, be left only with this part here, and here we can actually do the argument that we want to do. So the first one is kind of trivially satisfied, because for a point to be optimal, it has to be feasible. So this part here is actually 0. So this term cancels out. Now, for these two terms, remember that we introduced kind of the costates kind of arbitrarily, right? So we fictitiously augmented our cost function, adding 0, with these additional costate functions. So here we actually could choose the costate in a quote-unquote smart way in order to cancel everything out. And so this is exactly what we do. So we set the p's to be equal to this other stuff. And so we are left with only this term where the variations are arbitrary. And here we could do the argument that this thing has to be equal to 0. And so if you kind of think back at what the actual necessary optimality conditions were, these were exactly those conditions. So remember, we had two differential equations and some algebraic equations. The first one was that the dynamics need to be satisfied, and it's this term over here. The second one was a condition on the costate variables, and it's this term over here. And then the last one was that this term over here needs to be equal to 0. So I invite you to kind of do the mapping between these slides and the actual formulation, where the only difference is that we're being more elegant by defining the Hamiltonian. And this is all for today. Thanks.